Of the 7 basic measurements monitored by NIST, mass is the only one based on a physical object. The IPK and its replicas were forged in 1901. In 1989, physicists charged with maintaining it claimed the artifact had changed by as much as 50 micrograms. It doesn't sound like much. In fact, it's about the weight of a grain of salt. But that shift was more than enough to have groups reliant on accurate mass measurements worried about the consequences.
We metrologists are very greedy in our measurements. We like to keep track of every microgram, of every fraction of a microgram if we can. So we can detect things with very high precision so that you know what you're buying and you know what you're measuring exactly.
The Mass and Force Group at NIST has set out to minimize the slight instability in the mass of the kilogram.
The main thing that needs to be done is one needs to have a definition that is not based on an artifact, because then you eliminate all possible sources of instability.
There's a worldwide effort dedicated to relating the kilogram to phenomena that exist in nature, like those for length and time. These projects involve complicated calculations, but suffice to say, the Avogadro project will attempt to count every atom in a new kilogram artifact. The Watt balance will try to define it with electronics.
We want to create the most perfect measurement that can exist, that we can trust for long times to come.
After all, 50 micrograms probably won't make a difference when Shamu gets on the scale. But it may affect the exacting method by which pharmaceutical companies manufacture drugs. It takes a large scale to measure the weight of a whale. But to take the temperature of your chicken or turkey dinner, all you need is this ingenious little device. In 2005, a team of Caltech scientists built the world's most sensitive scales. They can weigh a few zeptograms, or the approximate mass of 1 protein molecule. Measure It will return on Modern Marvels. We now return to Measure It on Modern Marvels. We know when it's hot, and we know when it's cold. But we need thermometers to quantify temperatures with precision. They recorded the hottest temperature on Earth at 136 degrees Fahrenheit, and the coldest at minus 128 degrees. And this man has over 3,000 of them.
We're in the little Cape Cod village of Onset, Massachusetts, which has now been named the thermometer capital of the world, because I've had as many as 5,100 thermometers pass through the museum. Started about 25 years ago. Why? Someone had to do it.
Dick's collection spans all 7 continents and includes examples of almost every type of thermometer ever made. This one uses a human hair to detect humidity. This one is a thermocouple. And this one can help you calculate wind chill.
This type was invented by the engineers that worked with Frank Perdue, the Chicken Man. The way this one works is a fusible plug, which is simply a material that melts at a certain temperature, in this case around 160 degrees, and when it does melt, it releases a little spring that pops up the red arrow.
John Glenn swallowed one like this when he went back to space in 1998.
The interior parts of this would be a radio transmitter, a battery, and of course a very small thermometer.
Galileo invented one of the first thermometers in 1593, but its measurements weren't very exact.
This one's called a Galilean thermometer for Galileo. You can see I've got 6 balls here, and they're all immersed in liquid. That liquid is going to change its buoyancy as a function of temperature.
Each colored ball is filled with a slightly different amount of alcohol. Since alcohol is less dense than water, the balls float. But as the temperature outside increases, the density of the water decreases. That causes the balls to sink.
By counting the number of balls remaining, you have an idea of the temperature. You can say, oh, it's a 4-ball day, or a 3-ball day, a 2-ball day.
100 years after Galileo's thermometer, Daniel Gabriel Fahrenheit came up with the first numerical temperature scale. It had 3 arbitrary fixed points: 0, 32 degrees for the freezing point of water, and 96, which was the temperature of his wife's armpit.
About 20 years after Fahrenheit made his thermometer, Celsius made a different scale. 0 on Celsius's scale was the ice point. 100 was the boiling point of water.
Because it's based on multiples of 10, like the metric system, Celsius became the temperature scale of choice in 1887. But Fahrenheit still has some fans, including the United States. Fahrenheit took his measurements with mercury in glass, which was very conducive to temperature change.
Mercury responds to a change in temperature more quickly than other liquids. The thermometer freezes at minus 36 degrees Fahrenheit, but it does go over 1,000 degrees. It is a very usable but a very dangerous liquid.
Today, many thermometers are made with alcohol or kerosene. They work the same, minus the health hazards. NIST establishes its calibration standard with something called a water triple point cell.
This is a cell that has only very pure water in it. Up here, there's no air, it's a vacuum.
When water exists in all 3 phases of matter, it's at the triple point.
Whenever we have those 3 phases coexisting, then that nature conspires to lock that down at a single temperature. We've assigned that temperature to be 0.01 degrees C. This is the point that defines the Kelvin.
The Kelvin is the NIST standard, and they use it to design hyper-accurate thermometers.
We have a standard platinum resistance thermometer right here. This is one of the most accurate thermometers in the world. This thermometer can measure up to 420 degrees C. This thermometer uses pure platinum wire, where you measure the resistance of that wire that changes as a function of temperature.
The digital thermometer in your medicine cabinet uses the same principle and achieves accuracy within 1/2 degree. Platinum resistance thermometers are the instruments of choice for measuring the temperature of everything from the core of a submarine to lava to your home oven. Grains of wheat to kilograms, sundials to atomic clocks, the length of a human foot to the speed of light. As we strive to calculate more perfect measurements, the units we use to define them may change. But what won't change, whether it's length, speed, time, weight, or temperature, is our need to measure it.